trig functions, log functions, exponential functions, natural logs. Oh, you have to wait to find out. Just to recall, the reciprocal of the number x for any real number is 1 over x. That's what you're doing when you flip and take the reciprocal when you're dividing fractions, is you're actually taking 1 over the fraction. So when you're asked to graph the reciprocal of a function y equals f of x, this means you will graph y equals 1 over f of x. We're going to start with the most basic linear function, which is y equal x, and then we'll take the reciprocal and see what happens. So let's just get the first function. So if x equals negative 5 and y equals x, what's y? Negative 5. And if x equals negative 1? And if x equals negative 0.5? And if x equals 0? 0.5? F of x. Okay, so let's graph this line. Should be no surprise what it looks like. Negative 5, negative 5. Negative 1, negative 1. Negative 0.5, negative 0.5. 0, 0, 0.5, 0.5. 1, 1, and 5, 5. Doesn't matter. I always do it in pen so you guys can see it. Okay, so regular linear line, straight linear line from last year. Now let's take all those y coordinates and let's divide them under 1. So if I take negative 5 and I do 1 divided by negative 5, what do I get? So negative 1/5, which is approximately how much? So negative 0.2. 1 divided by negative 1, negative 1. 1 divided by negative 0.5. Easiest way in your head is to turn 0.5 back into a fraction. What's 0.5 as a fraction? 1/2. How do we divide fractions? Multiply by the reciprocal. So in this case, I'm going to multiply by negative 2 over 1, which will give us negative 2. One divided by 0. Ooh, whoa. 1 divided by 0. Does it exist? Not possible. 1 divided by 0.5. Well, same work as down here. It's just not negative. So we'll end up giving us 2. 1 divided by 1. And 1 divided by 5. Which is 0.2. Okay, so let's graph those new points. First one is negative 5, negative 0.2. So negative 5, negative 0.2. And I'm putting the dot really big so you can see where I put it. Negative 5, negative 0.2. Negative 1, negative 1. Not yet, but we're getting there. Negative 1/2, negative 2. Does not exist. Okay, let's skip that for now. 0.5 and 2. 1 and 1. And 5.2. So is our new graph linear? Definitely not. The first thing we're going to talk about is what do you do with a point that does not exist? That's when you grab your red pens. Points that do not exist graphically need to be shown somehow, and it's kind of weird to think to show something that doesn't exist. That's kind of weird. So mathematicians decided we would show something that doesn't exist by using a dotted or a dashed red line. A dotted or a dashed red line. Does it have to be red? Yes. Does red mean red? Yes. Red does not mean pink. It does not mean orange. It does not mean purple. It does not mean blue, black. It does not mean blue with a note saying this is red. It doesn't mean anything else with a note saying pretend this is red. Red means red. What do you need to bring to the final exam? A red pen. Red is red.
Do we need arrowheads?
Yes. Because that's what mathematicians decided.
Red equals does not exist.
Red equals does not exist.
I have red.
Yep.
You know the x-axis?
The reason they don't do it in a different color is because it could look like an inequality. Remember when we did linear equalities and we had the dashed line versus the solid line? So that could look like a linear inequality at that point, where red is clearly does not exist. To show a value that does not exist, which is an NPV or restriction, we use a red dashed line called an asymptote. An asymptote. I don't know if there's any other word that has an M, then a P, then a T in it. Asymptote. Oh, that's good. That's right.
Symphony? No, that's not the T.
No, not a T in there. Asymptotes are lines that you're going to come across practically with every single function in grade 12, and they're points that do not exist. What it means is a function or a line on the graph can come really, really, really close to that value. It can't cross it. Then you're going to find out next year that's a little bit of a lie. For now, it comes really, 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 really close to it. It won't actually cross it. So don't grab red, but go back to whatever you were using for the regular graph. The way these reciprocals look like is they approach the x-axis, cross through those 3 points that we have, and then approach the asymptote. They don't actually cross the x-axis. They don't actually cross the asymptote. I chose to do it in a different color. It cannot be red. That's all I care about. On the other side, it starts approaching from the asymptote, goes through those 3 points, and approaches the x-axis. Yup. I do have arrowheads. There's your first reciprocal function. Linear reciprocals always look like this. They're always in 2 pieces. They might be in the first and the third quadrant. They might be in the second and the fourth. It just depends on your line. They're always going to approach an asymptote, and they also always approach the x-axis. Now, this is weird. I'm supposed to only teach you about vertical asymptotes, which I just did. There they are. But there's something called horizontal asymptotes that magically I'm not supposed to talk about, but are going to appear out of nowhere next year. So I'm going to talk about asymptotes. That's right. I'm just going to go against what the government says and do it. There's a horizontal asymptote on the x-axis. Why? You'll find out next year. Will it always be on the x-axis? Yes, until next year. So just draw a horizontal asymptote on the x-axis. Yes. Just draw it on the x-axis. Yes, just draw it on the x-axis. Uh-huh. Uh-huh. Exactly. Thank you, Lindsay.
You know what? It's 3 marks just for drawing a dotted line, okay?
Here's some math humor for you. Remember, we're not really funny people. Thank you. Generally, mathematicians not so much. This one might be my favorite.
Oh my god.
Oh, that just makes me laugh.
Wow.
That's awesome. That's funny. That's funny.
It looks like the asymptote's crossing, or the thing is crossing the asymptote.
They're called asymptotes with a T, not asymptopes, because then you're thinking of isotopes from chemistry. Completely different thing. Okay? They're called asymptotes. Think like a tote bag at the end. Finding asymptotes.
Oh, so all we have to do is draw that extra line.
That's it. We're done. That's our reciprocal. Finding asymptotes. To find a vertical asymptotes, you take the NPVs. Little reminders, how do we find NPVs?
Anything that makes the bottom equal
So denominator equal to 0. NPV is because there's sometimes more than one. Oh, it's a little tiny s. Yes, ma'am.
Are we having quizzes or are we only having requests at the final?
I don't know. I thought we'd talk once we finish the notes and decide together.
Yes, we should go on a quest and then slay a dragon.
Horizontal asymptotes, again, we're not supposed to talk about them. We will. They're always going to be at y equals to 0 for next year. So that's on the x-axis. Yes. Was a little phlegmy there. It's not nice. So the first example, we're just going to practice finding the asymptotes. It's exactly the same as an NPV. So if this was a question from last unit, how would you find the NPV? So we would take
0 equals negative 5x plus 4. Solve for x. Okay. Now we can move the 4 to the other side. Yeah. X, and then x. 4 over 5. Yeah, 4 fifths. So x can equal 4 fifths.
And you'll often see the abbreviation VA in front of it. What do you think VA stands for? Vertical asymptote. And then we'll talk about the HAs next year, and what does HA stand for? Horizontal asymptote. All you need to know is that it's y not equal to 0 at this point. You'll figure it out more next year. Okay, so we want to be able to do this without table of values, so we're going to take the line 3x plus 6 and turn it into reciprocal. Draw the line for me first. So draw 3x plus 6. When you're done, just compare with someone, a little high five if you guys have the same line. Anyone gonna high five me? Anyone? Thanks this side of the room. Got my back. Not so much this side. So step number 1, draw the linear function. Draw the linear function. Step number 2, draw the asymptotes. Draw the asymptotes. I always start with the horizontal because it's like the idiot asymptote. It's never going to change till next year. It's on the x-axis. It has to be dotted and it has to be red. Yes. Again, technically we're not supposed to draw because we're not supposed to talk about it, but I could not draw a reciprocal graph without drawing it. It's like incomplete. It's like icing the sides of a cake and putting nothing on the top. It's just weird. It's weird. Yeah. I don't like that. Then we got to do the vertical asymptote. There's 2 ways that you can do it. You can take the original function, equate to 0, and solve. So let's do that method on the bottom. So method number 1, you can solve for it algebraically, which we just did. But what we just found was what on the graph? No, look at the graph. What's at -2? It's the x-intercept. That will always be the asymptote. So I never actually calculated. I put my ruler right where the x-intercept is, and I draw my vertical asymptote. So for the HA, it's always going to be at y not equal to 0. For the VA, it's going to be at all the x-intercepts. HA, y not equal to 0. VA will be right at the x-intercept. I'm going to ask the question, then I'm going to give you 30 seconds to turn and talk. So when I ask the question, do not blurt out the answer. With your partner, I want you to decide what are the only numbers that are their own reciprocal. What are the only numbers in the world that when we flip them, they go back to themselves? Turn and talk. Okay, what are the only numbers that are their own reciprocal? 1 and -1. So in your head, if you flip 1, what happens? You get 1. If you flip -1, you get? Flip it over. So 1 divided by imaginary 1, flip it over. What does it end up being? 1. -1, flip it in your head. What happens? -1. So 1 and -1 are really important points with reciprocal graphs because they're the only numbers that are their own reciprocal. We call them invariant points. Invariant points. Invariant means they don't change. So they're on the original graph, they're going to be on the reciprocal graph, they're really important points. So step number 3, mark the invariant points. Mark the invariant points at x equal to 1 and x equal to -1. I meant to say y. Why? It really bothers me I switched colors there by accident. And so now my left brain is, do I keep going in blue or do I go back to purple? I don't know what to do. I don't know. But then 1 and 2 are the same color. This is...
Go down to the rainbow. Like it's going to be there.
But if I have 2 purple, I should have 2 blue. Really? Us left brains really stress a lot, let me tell you. Here's the easiest way to mark the invariant points is put your ruler down at y equal to 1. Put your ruler down at y equal to 1. Wherever it cuts the main graph, so not the asymptote. I don't care about the asymptote. I'm looking at my line. Put a point there. My straight linear line, yes. Put your ruler at y equal to 1. Mark wherever it crosses the original graph. Scooch down to y equal to 1. Mark wherever it cuts the original graph. Because visual people, we need to have something to go across, otherwise we get mixed up with this. But well, do whatever you want. Don't use your, I don't care. Have I ever said you must do things my way? Yes. Only my way? Questions so far? Why are we using 1 and -1? Because they don't change. They're the only 2 points that are going to be on both the graphs. Step number 4, draw the reciprocal graph. Draw the reciprocal graph. I'm going to start on the left-hand side here. I know it's going to approach the x-axis. It's going to go through my invariant point and then approach the asymptote.
So
starts as close to the x-axis as you can get it. On the right-hand side, it's going to come down from the asymptote, cross through the invariant point, and approach the x-axis. Will it ever cross an asymptote? No, it will get really, 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 really close, but never actually touch or cross the asymptote. That's reciprocal graphs. Draw the original, draw the asymptotes, mark the two invariant points, figure out the graph. These are one of my favorite graphs to draw because they look so nasty. You're like, what is all that? Probably one of the easiest graphs. Let's practice. Like for asymptotes? Or the curve? No, it's just as close as you can get it. Like, for example, let me show you this, and don't do this, but you would never have a graph that looked like that, right? It's not going to pull away like that. It has to approach. So it kind of is like that really kind of steep, like, swoop to it. Okie doke, sketch the graph of 1 divided by negative 2x plus 6. State the domain and range. Somebody remind us about domain and range.
XCR.
But there's an asymptote.
XCR.
So it can't be XCR because there's an asymptote. Well, it can't be XCR because there's an asymptote, so there's a point that doesn't exist. That was absolute value graphs. We're on a completely different kind of graph now. Grab the bottom, graph the line. So just graph negative 2x plus 6. Put it in pencil because you're going to need to erase it in a second. High five me if you have the same line. Nice. Nice. I go to the vertical asymptote first, so I put my ruler down right on the x-axis, right where it crosses the x-axis, so the x-intercept. Draw the asymptote. Here's a little preview for tomorrow. What's the maximum amount of x-intercepts a quadratic or a parabola can have? 2. So how many asymptotes might we have tomorrow? Can't talk about it. Then I go right down on the x-axis and draw my horizontal asymptote.
Where would you use asymptotes in the real world?
All the time there's values that don't exist. Happens all the time. Then I put down my red pen and I grab my regular pen. I slide my ruler up to negative or to positive 1. Mark the point. So slide my ruler up to positive 1, mark the point. Slide your ruler down to negative 1, mark the point. I guess that's why I use a ruler, because I already had it in my hand.
Also, someone like me who can't draw.
Going to the left first, it's going to approach the x-asymptote, go through that invariant point, and then go up toward the asymptote. I used to describe this as shooting up until one day Mr. Pelche walked in as I was saying, please shoot up. It's like, maybe I need to not say that. On the right, it's going to come from the asymptote, cross through the invariant point, and approach the x-axis. There's your reciprocal graph. What do you do with the pencil or the original line?
But how do I know how to do it in the future?
What?
Like in the future, when I look back at my notes, I'm like, wow.
Then just make yourself a little note. I will erase this on the quiz or test or exam. Please erase this. Bring one. Try this one all by yourself. Oh, domain and range, domain and range. So look to the left. This little arrow here means what? Goes to negative infinity. What about the arrow on the right-hand side? But where is their not graph?
In the middle.
At x equal to 3. So here's how we state that. We start with xer, but then we put x cannot be 3. That's how we do it with an asymptote. So what that's saying mathematically is every single value except 3. What about the range? So look down. Arrow pointing down means negative infinity. Look up. Arrow pointing up means positive infinity. Where is there no graph? Right at 0. So how am I going to express that? Y. If you like the other notation, here's what it would look like. We would start with negative infinity up to 3 not included, and then 3 to infinity not included. That's saying the exact same thing, so all the way up to 3 and past 3 without including 3. This one would be negative infinity to 0 not included, 0 not included to infinity. Okay, so it's saying every value except for 0. Try this one on your own with the domain and range. Questions so far? So I put my ruler at -1 wherever it crosses that line, and then up at +1 wherever it crosses that line. Always, because they're invariant points. They're not going to change. They're going to be on both graphs.
And wherever it crosses, wherever your pencil line crosses.
Yes. Oh, kind of went a little wonky there.
Are you laughing at me for learning?
Oh, missed that dot. Let's pretend I didn't miss that dot. Oh, there you go.
Put arrows on both ends of the.
Yeah.
Oh, okay.
If you haven't already, write down the domain and range.
Pick up order 40 for signatures or
Gratuitous advertising. Domain? Range?
So will y not change?
Correct. Till next year. How are we feeling? Show me a thumb. Getting this? Good. Last example, we just need to be able to go backwards.
This is a curveball.
This might be easier than going forwards. This might be easier.
If I was up to that right now.
Okay, you guys tell me, so let's pick apart the method and go backwards. What's the last thing we did when we drew the reciprocal? Yes, domain and range, because it asked, but within the graph, what did we do? Okay, we did our dots where? Okay, and I think I already marked them for you. What do you know about those dots? They're on both graphs. Oh, but we also have another point we can mark.
The middle of when it hits the x-axis.
What do you know about the asymptote, the vertical asymptote? It's going to be the x-intercept of the line. So now we just draw the line. That's it. That would have been the original, so this would be f of x. So the reciprocal is 1 over f of x. This would be f of x. That's it. Draw a method. Or draw a method, write a method. Mark down what you did step 1, mark down what you did step 2. We're writing steps. We're writing steps.
What the heck?
I don't know. Find the x-intercept of y.
Okay, write that. You're writing your own, so whatever makes sense in your head.